Welcome to Homework Lib.
This is chapter 35, problem number 50. We have, this is a problem that talks about the camouflage in fish. So we have water layer, and then the platelets like guanine, and then finally we have cytoplasm. Obviously, each medium has a different index of refraction. Guanine has 1.8, cytoplasm has 1.33, just like water. Now, we are looking for the wavelength at which all the reflection would be in phase. So let's look at the interface of water and guanine. The reflected light undergoes a phase change by pi, and at the interface of guanine and cytoplasm, that doesn't happen because index of refraction of guanine is higher than the cytoplasm's, right? So whatever light reflects off here is not gonna have a it's not gonna undergo a phase change, so the overall phase change between the reflected lights is gonna be pi. So then, well, we're still looking at the constructive interference, so twice the thickness of the guanine is going to be equal to m plus 1/2 lambda over n guanine, right? So then lambda from here would be twice the thickness of the guanine layer times the index of refraction of guanine divided by m plus 1/2. So if we're looking for what happens when m equals 0, then the lambda we can calculate for it. The thickness of the guanine layer is given to us as 74 nanometers, so 9 meters. The index of refraction of guanine is 1.8 divided by 1/2. We find the wavelength to be 533 nanometers, so green. If we do the same for the cytoplasm, it's going to be 2, let's call it the thickness of cytoplasm layer, m plus 1/2 lambda divided by the index of refraction of cytoplasm. Then for lambda, we're going to have 2 TCNC over m 1/2. When m equals 0, this is going to be 0. So the cytoplasm layer is given to us as 100 nanometer thick. The index of refraction is 1.333, actually, one more 3, divided by 1/2. We also get 533 nanometers. So we have 533 as an answer. Now in part B, this is more like a conceptual question. We're asked to explain why the stack of layers of these platelets increase the reflection. Well, obviously by having many layers at each interface, more of the transmitted light, gets reflected back at each layer, and overall this increases the amount of the light that is reflected. This increases the R, right? For each layer, the portion of the transmitted light is being reflected back. So apparently up to 80% these fish can reflect the light that falls onto them, which is very high, obviously. So in part C, the color that is most, we're asked to figure out why the color that is most strongly reflected from a platelet depends on the angle at which it is viewed. So we need to find a correlation between the angle and the wavelength. Again, this is a conceptual question. Well, it's because at different angles, what we have different different lengths, right? Different path lengths. So if we have different path lengths, then due to this the difference in path lengths, then the wavelength will also the wavelength, the let's say lambda has to change, right? Has to change. Um, well, the lambda it interferes constructively if that's the particular color that is viewed from outside. So the reason for that is because we have different path lengths now at different angles. So of course, it's going to affect the lambda that is viewed.